Hello everyone. Welcome back to this lecture series on engineering mechanics. In the previous lecture, we studied Varignon's theorem and learned how to reduce a system of non-concurrent forces into a single resultant by equating moments. Today, we move on one step further and study a very important special force system known as a couple. So couples are extremely common in real engineering applications, and understanding them properly is essential for solving many numerical problems in engineering mechanics. Let us begin with the definition. So a couple is a system of two equal and opposite forces acting on a rigid body such that the forces must be parallel, they must be equal in magnitude, and they should be opposite in direction, and the line of action are not collinear. Because the forces are equal and opposite, the resultant force is zero. But the forces still produce a rotational effect. Hence, the effect of a couple is pure rotation without translation. So, the perpendicular distance between the lines of action of the two forces is called the arm of the couple. For example, here you can see we have a two forces P and Q. Let that both the forces be of same magnitude but acting in the opposite direction. So epsilon is the distance between the two forces, the perpendicular distance AB represents the arm of the couple. So the moment of the couple is given by M is equal to F into D, that is force into the perpendicular distance between the line of action of the two parallel forces. Now let us understand this concept physically. So in day-to-day life, we encounter couples frequently. For example, opening or closing a water tap, turning the cap of a pen, twisting a screwdriver, or even steering a motor car. So in all these cases, your hands apply two equal and opposite forces. So the object rotates without translating. This is exactly the effect of couple. Now let us solve the first numerical problem shown in the slide. So several forces are acting at different points and angles, and we are required to replace the given force system by an equivalent single force applied at a point O. So here, since the forces are acting in different directions, so obviously we need to resolve the forces. So here, the angle of this 20 Newton degree is 30 degree with respect to the horizontal. Similarly, this 50 Newton is inclined at an angle of 60 degree with the horizontal. So if I am resolving means it will have its horizontal component in this direction. The vertical component will be in this direction. Similarly, this also resolving means you'll be getting the vertical direction in this one, and horizontal component will be in this direction. So since the angles are given with respect to horizontal, so therefore the horizontal component will be cos theta. That is here, this one is 20 cos 30 degree. And this will be 50 cos 60 degree. So since the horizontal components are cos, vertical components will be sine. So this will be 50 sine 60 degree, and this will be 20 sine 30 degree. So now we got the resolved components of all the forces about x and y. Now let us sum up all the forces in the x direction as well as sum up all the forces in the y direction. So if I am summing up all the forces which are acting in the x direction, we will be getting minus 20 cos 30 plus 50 cos 60, which will comes as 7.68 Newton positive, which means that the net force acting in the x direction will be acting in the right side direction. Now let us move with the vertical force. So vertical force Fi will be 25 is acting upwards, so positive, 15 is acting downwards, negative, and then these two vertical components are acting in the downward direction. So minus 20 sine 30, minus 50 sine 60. So you are getting the net value as negative. So which means the summation Fi will be acting in the downward direction. That's what has been represented here. So we don't know where it is acting. Let the resultant be calculated by using the parallelogram law of forces, which is root under fx square plus fy square. So I am getting that value as 43.98 Newton. Similarly, the direction of the resultant will be calculated by using the relation tan inverse fy by fx. So we are getting that value as 79.94. So we are representing the resultant, that is R, which makes an angle alpha with respect to the horizontal. So this is what is the alpha. Let us assume that the line of action of this force is going in this way, so that the perpendicular distance from the line of action with respect to point O, because here it has been asked that we need to convert this force system into an equivalent single force system that should be applied to the point O. Therefore, we need to find the the perpendicular distance from the line of action of this resultant towards the point O. Now, calculating the moment of all these individual forces about the point O, because we need to find the position, in the sense we need to apply the Varignon's theorem. So as per Varignon's theorem, we know that moment of all the individual forces about a common point will be equal to the moment of the resultant of all those individual forces about the same common point. So in that case, we are going to assume O is the common point where we are going to find the moment. So this 25 Newton force is not passing through the point O, so it tends to rotate about the point O in this direction, that is anti-clockwise direction. So in that case, it will be 25 into 2. So that will be positive. So 25 into 2, positive. Now we shall move with the 15 Newton force. 15 Newton force is acting right side in the downward direction. So if I am rotating this force about the point O, it tends to rotate in the clockwise direction. So that value will be minus 15 into 3 plus 2 will comes 5. We shall move with the vertical component of this 20 Newton force. Again, that is also acting on the right side of the point O. When it is rotated about the point O, it tends to rotate in the clockwise direction. So that will create a moment about the point as negative since it is clockwise. So minus 20 sine 30 into the distances 4 plus 3 plus 2, which is 9 meter. And then vertical component of the 15 Newton force. So that is also acting right side downward direction. So it tends to rotate in the clockwise direction about the point O. So that also will be negative. So minus 50 sine 60 into the total distance from this point to O is 6 plus 4 plus 3 plus 2, which is 15. So that's it. We got all the moments. So for this horizontal component is 20 cos 30 as well as 50 cos 60. The line of action of these two forces passes through the point O. So hence they won't create moment about the point O. So that is what has been given here. So 25 into 2 minus 15 into 5, then minus 20 sine 30 into 9, and then minus 50 sine 60 into 15. So that is what is the net force of all these, net moment about O of all these individual forces, which comes as minus 764.52, which is clockwise, since it is we are getting a negative. So now take the resultant. Resultant is acting on the right side downward direction. If I am rotating this resultant about the point O, means this also tends to rotate in the clockwise direction. So that will also be negative. So as per Varignon's theorem, R into D will be equal to the moment of all the individual forces. So that is what R is 43.98 into the D we don't know is equal to 764.52. So both the sides negative will be that. That's why it has been removed. So solving this one, we'll be getting D is equal to 17.38 meter from point O. Right. Next, our question is not to find out the distance, because we need to replace this all these four forces into a single force about the point O. So for which what you are going to do is apply the resultant force about the point O in opposite directions like this. So the net effect will be 0. Now this one and this one both are in same magnitude acting in the opposite direction. They are parallel forces separated by a distance d. So this will forms a couple. Right. So the moment of the couple will be R into the D. So R is 43.98 and D is 17.38 that we have calculated recently. So substituting that value, we'll be getting the moment of the couple as 764.37 Newton meter. So it tends to rotate in this way. So it's a clockwise couple. So this 2 can be now removed thereby introducing a couple at that point. So the remaining will be this alone. So representing that one in the given figure, so I'll have the resultant which makes an angle alpha with respect to the horizontal, and now this 2 has been replaced with a couple. So 764.37 Newton. This is what the question has been asked. So we just resolve that forces into a single force system over the point O. Okay. So we'll take one more example. A rigid bar AB is subjected to a system of parallel forces shown in figure. Reduce them into a equivalent single resultant and then force moment system about point A, D as well as B. So totally 4 things has to be found out. Now in this case, fortunately, all the forces are acting in the vertical direction. So if you want to find out the resultant in the sense, resultant also will be acting in the vertical direction. So that will be 15 minus 40 plus 30 plus 20. So you'll be getting the resultant value as minus 15, which means that the resultant will be acting in the downward direction. Let me assume that resultant may be acting somewhere here, which acts at a distance L from a reference point A. Okay, so now let us calculate the moment of all the individual forces about the point A. So 15 kilonewton is acting at that point itself, so it won't create moment about the point A. Whereas 40 Newton tends to rotate about the point A in the clockwise direction. So that value will be minus 40 into 1. Similarly, D, it is acting right side upward direction, so it tends to rotate in this direction, that is the anti-clockwise direction about the point A. So that value will be 30 into the perpendicular distance is 2 plus 1, 3. This is a positive one. And finally, this 20 Newton force, it is acting on the right side of the point A. So it tends to rotate in this direction, that is a clockwise direction about the point A. So that value will be negative. So minus 20 into the perpendicular distance is 2 plus 2 plus 1, 5. So that's what has been represented here. So minus 40 into 1 plus 30 into 3 minus 20 into 5, which comes 50 kilonewton meter clockwise. So as per Varignon's theorem, we know that R into D will be equal to the moment of the individual forces. That's what has been written here. So 15 into L will be equal to 50. And again, similarly, minus and minus has not been written here. So both will be getting nullified. So that L is equal to 3.33 meter from the point O. So this is what has been calculated. So 3.33 meter. So first thing is over. That is single equivalent force has been calculated. Now we need to reduce this into a force moment system over the point A. So now we calculated the resultant, which is acting at a distance 3.33 meter from A. So we need to reduce that one to the point A. So again, produce the same force at the point A in opposite directions. So now this and this will form a couple because both are same in magnitude, opposite direction, parallel, separated by a distance 3.33 meter. So these two moment of the couple will be R into D. That is nothing like 15 into L in this case. That is this one will create a clockwise couple. So that will be 15 into 3.33 will comes 49.95 Newton meter clockwise. Okay. So unfortunately this has to be kilonewton. Right. So representing that one, the remaining is only this 15 kilonewton. So you can produce that one. So 15 kilonewton and these two has been replaced with a couple, clockwise couple of 49.95 kilonewton meter. Okay. Now let us move with the force moment system over the point D. So since it is this resultant is acting at a distance of 3.33 from A, so from point D that is only 0.33. So now we need to replace this one at the point D in the opposite direction. Again, now this and this will constitute a couple. Both are acting in the opposite direction with the same magnitude separated by a distance 0.33 meter. Right. So the moment of the couple will be R into D. That is nothing like 15 into 0.33, which comes as 4.95 kilonewton. Again, kilonewton meter. It's a clockwise moment again. Right. So representing in that figure, so I'll be getting 15 kilonewton at the point D as well as a couple of, that is a moment of 4.95 kilonewton meter. Next, the final condition is we need to reduce the system into a force moment system about the point B. So now the total distance what we calculated from A is 3.33 meter. So total is 5 meter. So 3.33 reduced, we'll be getting that value as or that one 1.67 meter. So now we can reproduce this resultant about the point B in both the directions. So 15 kilonewton and 15 kilonewton. Now this and this will constitute a couple. Both are equal in magnitude, opposite directions, separated by a distance of 1.67 meter. Right. So that is what. Now in this case, this will constitute an anti-clockwise couple. Tends to rotate in the anti-clockwise direction. So moment of the couple will be R into D, that is R into L. So which is 15 into 1.67, which comes as 25.05 again kilonewton meter in the anti-clockwise direction. So representing in the figure, you'll be getting about the point B. This is the only thing remaining. So 15 kilonewton and an anti-clockwise couple of 25.05 kilonewton meter. Okay. So in this way only, the couples will be calculated, or we can reduce into a single force couple system. Okay. So let us summarize this today's lecture. So a couple produces a pure rotation. Resultant force of a couple is 0. So moment of a couple is independent of the reference point, and Varignon's theorem allows us to reduce complex force system. In the next lecture, we'll move on to the forces in space, where vector approach will be followed. Thank you.